So I work in the University of Leeds in the Leeds Institute for Cardiovascular and Metabolic Medicine, but that's a predominantly basic science institute with a small epidemiology section. So I sit in the Leeds Institute for Data Analytics, which has got close links with the Turing Institute, and it's similar to here, a kind of open, collaborative environment to work in, so it's quite a nice place to be. I'm currently funded on a Sir Henry Wellcome fellowship, and some of the work that I talk about here is previously being completed as part of British Heart Foundation project grant funding. So I was asked to talk about making the most of health data, the current landscape, the challenges and opportunities, and to provide some examples from my own work. So why did they ask me, you might wonder? Well, because I came last time and I said yes, so that was the first point. I've got a background in mathematics and statistics, which I studied at the University of Sheffield. I then went on to become an epidemiologist at the University of Leeds, and I've spent the last 10 years or so working with a range of different health data. So initially in cancer epidemiology and subsequently in cardiovascular disease. I've worked with primary care data, national hospital episode statistics data from NHS Digital, as well as disease-specific registries from NICOR and the National Cancer Registration Service as well. So I think that puts me in a good position to give you an overview of making the most of health data. We shall see. So there's obviously a lot of excitement about the power of data to transform healthcare. A quick Google gives you lots of blue, exciting images. I don't know why these are always blue, but anyway, that seems to be a recurring theme. But some people take a bit more convincing. So in 2016, there was an editorial in Circulation talking about the hype or reality of big data to improve healthcare. So there are still people out there who have their reservations, and probably rightly so. So they say substantial challenges still exist in terms of transforming big data insights into meaningful healthcare improvements. There are regulatory and privacy concerns, and they mostly talk about the fact that healthcare data are observational, so there are a range of statistical problems such as species correlations, bias, and unmeasured confounding that could occur. So their sort of take-home message was clearly the conversion of big data hype to reality still takes significant work. So I agree there are a lot of challenges, and a lot of them have been mentioned already. Access to data, issues with the sort of unstructured nature of routine healthcare data, which is not designed for research specifically, and the complexity of the size of the data, some of the biases, missing data. There could be selection bias, there could be unmeasured confounding, there could be lots of correlations that aren't actually really clinically meaningful, especially when you get to huge size of data, you're more likely to find these correlations. So if we're not looking at observational data, we're left with maybe randomized control data, which I do feel still are the gold standard for looking at treatment efficacy, but they're conducted in very controlled clinical environments. They've got very strict inclusion and exclusion criteria. They're not always feasible or practical or cost effective for the particular research in mind. So it could lead to questions still over the representativeness of the outcomes, the generalizability from some of the randomized control trials. So I do think there's a lot of opportunity with big data. Observational healthcare data can provide knowledge on large populations, really in real-world clinical settings. So you don't have the strict inclusion-exclusion criteria of controlled trials, so perhaps we're picking up more representative real patient samples. It can help identify areas for improvement in care, and something Harry was talking about in terms of looking at guideline adherence. We can use those data as best we can to actually provide a scientific basis back to the clinicians about how well or not they are using those guidelines in general practice. and maybe convince them that they perhaps should be used more or not in certain areas. And it could lead, there's lots of stuff from observational data that can lead to the development of new clinical trials as well. Maybe smarter designs of clinical trials, different outcomes that could be obtained from observational data that can then go on to develop into a new clinical trial. But we need expert knowledge of the specific datasets used to be able to achieve all that, and the application of appropriately advanced techniques to overcome some of the challenges. So I'm just going to talk about a couple of research examples from my earlier work done as part of British Heart Foundation project grant funding using MyNat data. So this is the Myocardial Ischemia National Audit Project database. It's a comprehensive clinical database of acute myocardial infarction. It's got over 100 different clinical and demographic variables. It covers all acute NHS hospitals in England and Wales, and it's linked to ONS, all-cause mortality data. The specific extract that I've used for the two examples that I'll go through are admissions from 2003 to 2013 and contain just under 700,000 patients with a follow-up of almost 8.5 years. So I'm just going to talk about some of the methods that I've used to overcome some of the challenges. I definitely haven't overcome all of the challenges that are occurring in observational healthcare data. And I'm kind of skipping a few steps, but I'll try and guide you through as best I can so that you get a good overview of what kind of thing I do. So the first example is a piece of work published in the Journal of American Medical Association in 2016, in which we looked at temporal improvements in survival. So the premise for this is that we know there are substantial declines in mortality following acute myocardial infarction over recent decades, but actually very few people have tried to look at exactly what it is that has accounted for these improvements over time. So there's several possible reasons, including people might say there's been better use of adherence to guideline therapy. There could have been patient demographics over time that have led to these decreases, or actually are patients changing in terms of their clinical risk and representation, and has that led to the improvement in survival? So lots of people have looked at those individual factors and their effect on long-term survival, but not how did those individual things change over time and therefore impact on the temporal trend in survival. So that's what we try to unpick. So I'm going to jump straight into the modelling that we did for this, but before that there was a lot of processing, cleaning of data, multiple imputation to handle missing data as well. But I'm going to go straight into with the main modelling analysis that we did. So we used flexible parametric survival modelling, which is slightly more advanced than a standard Cox model, which doesn't have the issue of proportional hazards assumption required for normal Cox modelling. First of all, we looked at whether or not there was indeed an improvement in survival in our data set, and there was, as we'd expect. So this is just looking at the effect of time on survival, showing a 3.2% average annual improvement over time. We then looked at seeing how much of those other factors that we're interested in accounted for that temporal improvement or not by incrementally adding them to the model. So you can see with clinical risk, patient characteristics, comorbidities, and pharmacological therapies that after adjusting for those, there still remained some temporal improvement, which alludes to the fact that those factors don't wholly account for this temporal improvement over time. So the size of the improvement did go down slightly, but there's still some temporal trend going on after these factors have been taken into account. However, when you account for the use of an invasive coronary strategy in these patients, the effect was actually reversed. So that goes to, that can be interpreted to show that that actually accounted for the temporal trend. So once we've accounted for all these things, the trend was no longer there. In fact, it was reversed. So that was kind of my standard statistical approach coming from my maths and stats background. And I would have happily left it there, but then that's not quite thorough enough in terms of the science. So to publish in JAMA, you need to do obviously a lot of check-in to make sure your results are robust. So we did several other things to have a look at this. One of the main things was to look at mediation analysis, which is a causal inference technique. And this method allowed us to see how much of the trend was actually accounted for through these different pathways. So we looked at the amount of temporal improvement that was mediated by the invasive coronary strategy, and we looked at how much of it was mediated by the pharmacological therapies. And this largely confirmed our results, showing that most of the improvement in survival was mediated through the invasive coronary strategies at 88.3%, and a small amount was mediated by the change in treatments over time. So this is all about the change over time, not just those individual impacts on survival. So that nicely confirmed our original findings. And then, because this is observational data, there's a high chance of selection bias. So things that might not be measured in the data in terms of how likely someone was to receive an invasive coronary strategy. So we did an instrumental variable analysis, which is one of the techniques you can use to kind of mimic the randomization that happens in a randomized controlled trial. So we look at hospital rates of angiography and use this as a way to effectively randomize the patients back to treatment groups and then see what impact that has on the results. So that's one of the main challenges of observational data, so the possibility of selection bias, and this is one of the ways you could start assessing that and unpicking it slightly. So the standard analysis showed that the use of an invasive coronary strategy on survival had a 61.7% relative decrease in survival. But when we used the instrumental variable analysis, this was reduced to 46%. So that just goes to show there is quite a large selection bias, but that 46% is still meaningful. It's still a large impact. So this is just one of the examples of the types of methods you could be implementing to kind of overcome some of the challenges in observational data.
So is that decrease in mortality, hopefully?
Sorry, decrease in mortality, yes. Increase in survival, well spotted. So then one of the other studies I want to talk about is looking at multimorbidity in survival for patients. So again, it's the same data set of 700,000 patients. And this is something that's been touched on a lot by the other talks as well, looking at redefining disease. So not just thinking about cardiovascular disease or acute myocardial infarction as one thing, but looking at multimorbidity and seeing if there's certain clusters of disease that might tell us something interesting about the patients. So the background to this was that we already knew 2/3 of AMI patients have got at least one additional comorbidity. Interestingly enough, we talked about patient involvement earlier, and I invited a heart attack patient along to talk to me, hopefully about multimorbidity, but then she told me she does not have any other conditions, so she's possibly one of the 1/3, or it could be something about her understanding about which kind of conditions we mean. And sometimes you talk to patients and they go, oh, by the way, no, I don't have any other conditions, but oh, I do have diabetes, or it's quite interesting, illuminating talking to patients, and it does make you think about what it's all about again as well. Anyway, so a lot of the previous research has looked at individual comorbidities with AMI and their impact on survival or increased mortality. Lots of people look at composite measures, so they simply kind of count up how many conditions people have, but that loses the sort of detail about specifically which conditions. So 2 of one thing might not equate to 2 of another thing. There's quite limited data on sort of the complex interaction between different conditions. So we wanted to investigate the sort of multimorbidity clusters across a range of pre-existing long-term health conditions and see how they were associated with long-term survival for patients with acute myocardial infarction. So of the cohort, we found that 60% had at least one of these other long-term health conditions, and 42% of those had more than one long-term health condition. We looked at hypertension, diabetes, COPD, cerebrovascular disease, peripheral vascular disease, chronic heart failure, and chronic renal failure. And these are it's just summary stats on those. if you were going to do a simplistic approach, you might think, right, I'll look at all pairwise combinations. You'd soon be looking at 27 different categories. You could take it a step further and look at every single combination of every single number of diseases, and you'd have 127 different ones, even for those 7 ones of interest that we wanted to look at. So instead we use the latent class analysis approach, which is a modelling approach to sort of classify similar patients into groups. And this method provides kind of conditional probabilities of people ending up in a certain class as well. So the results of that showed 3 different clusters, which we then labelled as a highly multimorbid class, a medium class, and a low multimorbidity class. So this still keeps the kind of granularity of detail in that we've looked at all 7 conditions all at the same time, but it starts being a lot easier to interpret than 127 different categories. So we've got in the high multimorbidity class patients with heart failure, peripheral vascular disease and hypertension largely, but also some of the other conditions. And you can then start looking at the survival differences between those groups, and the differences are quite large. So the highly multimorbid group have got very poor survival rates in the long term. So this is all very exciting, but the downside of this work is that it was based on a clinical registry, so very specific acute myocardial infarction. And whenever that database was set up, MyNap database was set up, someone, not sure who, decided that it was those 7 conditions that they were going to record as the patient came in with a heart attack. Did they have any of these existing conditions? So the part of my fellowship, which is not presented here, unfortunately, because it's too early on, but is to look at routine electronic healthcare record data and really see what's going on without this prior sort of clinical bias in a way in terms of which conditions people think are important, and really to look at the disease trajectory following heart attack. So there are challenges, but there are also quite a few advanced techniques that can help you overcome some of those challenges. It really requires multidisciplinary teams, and that's what everyone said so far. Expertise of the specific data sets, expertise of a range of different techniques, not just one technique. You know, you need to check things that are robust by doing them in several different ways. It increasingly requires more programming skills as the requirements and methods are getting more complex, and sometimes the ready off-the-shelf packages haven't been developed to do those specific methods, in particular kind of this time to event data. You know, a lot of fancy methods are out there, for instance, instrumental variable analysis, but then they've not always been developed properly for time to event data, so you have to make assumptions and your own programs to do those things. And of course it requires clinical expertise, and it does help talking to patients, even if the particular patient that I talked to didn't quite have the experiences that I was hoping they would. So I need to do more in that sense and get a wider group of people together. And just finally, just some acknowledgements. Some of my team in Leeds, just the people that I could get together for the photo. There are more of us, but we can't get each other in the same room at the same time, unfortunately. Lots of external collaborators, and I always like to thank peer reviewers as well, particularly the ones for the JAMA work, which spent a lot of time really improving the sort of integrity of the work that was finally published. Thank you very much.
Thank you very much. Thank you. That's great.